If we consider this normal distribution with its mean at mu, it has a standard deviation, which, remember, is the square root of variance, which we'll call sigma. If this is x, we say it follows a normal distribution with mean mu and variance sigma squared. Looking at some of the features of this curve, it goes on forever in this direction. The negative x-axis is an asymptote. Remember that this means that the curve gets closer and closer to the x-axis, but never gets there. And the same is true for the positive axis. The curve goes off to infinity and never ever reaches the positive x-axis. The area under this curve, which is shaded in the diagram, all the way from minus infinity to infinity, is equal to 1 unit. And this is a very important feature, since it qualifies this curve as a probability density function. We know that the probability of a certainty is 1, and the area under this curve in its totality is 1. If we now consider the curve, where x is a random variable following a normal distribution with mean mu and variance sigma squared, and these points are A and B, then the probability of x being between A and B is given by the shaded area. The problem that we have here is that to evaluate this area, we need to integrate the curve. If we call the function that produces the curve f of x, the normal curve is very hard to integrate, most certainly beyond A level. To get around this, we use the following idea. We define z, which has a mean of 0 and a variance of 1, and we call this the standard normal. We have tables for the standard normal. They should be in your set of statistical tables. The way that these work is that for some value z equals a, the tables give the probability of z being less than a. In other words, what they give is the area shaded here from z equals a all the way back to infinity. As we'll see later, any normal curve can be transformed onto the standard normal, and so using tables we can work out probabilities for any normal curve without the need to integrate.